Now that we've taken some time to think about logic computationally and in other ways, we're going to go back to proving theorems, proving statements. So we're going to look at what we call direct proofs of theorems. And in particular, we're going to look at divisibility of integers as a part of math that we're going to prove theorems about. So we're first going to review how proofs of conditional statements work. We're going to extend this reasoning to all proofs. We're going to discuss where assumptions come from, because those are really important in proofs. We're going to define divisibility, and then we're going to do an example proof. All right, so let's remember how we prove conditional statements. And just remember, a conditional statement is a statement of the form if some statement, then some other statement. If P, then Q. So here P and Q are statements. So our proof looks like the following. We assume that P is true, and then we show that Q is true. And what you will find is no matter what kind of proof techniques we use throughout the semester, every proof is going to have these same elements in some form, right? There's always going to be something you assume, always something that you have to show. And so this is kind of like conditional statements are a model of how we do proofs in general. Every proof is going to be like proving a conditional statement. There are things that you assume in your proof and conclusions that you have to show. And all logic flows from the things you assume to the conclusions. And what is super important in all proofs is you cannot prove anything without assuming something. You cannot prove something just out of thin air. There's no such thing as proving something from nothing. All right, so we should talk then about where do these assumptions come from, right? Because if we're going to have these assumptions, we should be very transparent about where they come from, why we assume what we assume. Sometimes these assumptions are explicitly stated in the theorem. They are literally part of the theorem in anything that is either a conditional statement or can be thought of as a conditional statement. So here's a theorem. Let n be an odd integer, then n squared plus 3n plus 4 is an even integer. And look at that first sentence. Let n be an odd integer. It's screaming at you, we are assuming that n is an odd integer. That means you're allowed to assume it. Not only are you allowed to assume it, the theorem says we are assuming it as part of the theorem. So that's one place that you get assumptions come from. It's very explicitly stated in the theorem. Others are a little bit more implicit. So for instance, sometimes you get assumptions from definitions. So when I say let n be an odd integer, there's also some assumptions behind that if we say n is an odd integer, we get to assume the official definition of odd integers, right? So in just saying that n is an odd integer, that means, yeah, you can use the official definition. However, what it does not say you're allowed to get to use any intuitions you have about the definition. If you have some special insights about odd integers that you want to use in your theorem to justify some of the things you say, you can't just assert them because you are a math genius or whatever. It's not to say you can't use them, but if you want to use them, you have to prove them first. Axioms are another one that is implicit in a lot of the things that we do. We've actually used some of these before. These are statements that we accept without proof. This may make you uncomfortable. It's like, well, we get to assume stuff we don't have to prove. That doesn't seem right. But again, you can't prove anything without assuming something, so sometimes you need axioms in order to prove anything. So we've actually already done this in small ways. For instance, we assume that natural numbers are closed under addition and multiplication. We didn't assume that, or we didn't prove that, right? We believe it very strongly. It's baked into how we construct natural numbers, but we are actually assuming that as an axiom. And similarly, we're assuming that integers are closed under subtraction. Again, we never proved that, but we are assuming it for the purpose of proving our theorems. There are other places where the axioms, the list of axioms is a little bit more explicit. When you start working with proofs in Euclidean geometry, there are literally 5 axioms that you start with that you have to use in order to prove things in Euclidean geometry. One of which is that between any 2 points there is exactly one line. You might think this is a universal law with everything, but there are types of geometry where that is not only is that not assumed, but you can't even prove it. It's not true. All right, so now that we've gotten an idea of how proofs work and how all proofs somehow get turned into you assume stuff and you show stuff, now let's talk about some more math that we can prove about. Remember, we can't just prove stuff about math without any topics that we can actually prove stuff about. And we've already proved stuff about even and odd numbers. We're going to stretch out a little bit and talk about divisibility. Now, before we define divisibility precisely, I'm going to give you a model about what divisibility is like. And I call this model the no remainder model. It's not a very clever name. If you got a better one, I'm open to suggestions. So if I say that m divides n, that means we can divide m into n evenly. When I say we divide m into n, that means we do n divided by m with no remainder. So when we divide m into n or do n divided by m, we get no remainder. And the way we write this is m vertical line n. So when I say m vertical line n, that means m is divided into n, or we do n divided by m. And we get no remainder. So for instance, I do this division problem, 12 divided by 4 is equal to 3. I did 12 divided by 4. I got no remainder. That means 4 divides into 12. I get 12 divided by 6 equals 2. I divide 12 by 6. I get no remainder. Again, that says 6 divides evenly into 12. And if I want to write that, that says 4 divides into 12. 4 divides 12, and 6 divides 12 as well. And again, 4 divides 12 because when I do 12 divided by 4, I get a whole number. And when I divide 6 divides 12 because when I do 12 divided by 6, I also get a whole number. I also get an integer. No remainder. All right, so actually another way of saying this, and this is going to be a little bit easier for us when we actually define a definition. Every division problem can be restated as a multiplication problem, right? So I say 12 divided by 4 equals 3. Another way of saying that exact same thing is that 4 times 3 is equal to 12. And if I say 4 times 3 is equal to 12, I can also conclude that 4 divides 12. And if I can say 6 times 2 is equal to 12, that also tells me that 6 divides 12. But of course, it is not true that 5 divides 12, because if I divide 5 into 12, I'm going to get a remainder of 2, right? And if I get a remainder of 2, that is not 0, and so we get a remainder, and so it does not divide, 5 does not divide 12. All right, so here's the definition, the official definition of divisibility, and we kind of have two choices. We can have a division form of divisibility, or we can have a multiplication form of divisibility. However, it turns out the multiplication form is going to be a lot easier to apply in real life, and so that's the definition we're going to use. So let m and n be integers. We say that m divides n if n is equal to m times k for some integer k. Right? So we're doing n divided by m and getting no remainder. That's the same as n is equal to m times an integer for some where k is an integer. And there are other ways of saying the same thing. We've been saying m divides n. We can also say n is divisible by m. We can say m is a divisor of n. And we can say m is a factor of n. Oh, also we can say n is a multiple of m. Are we done now? I think that's all the ones we have. There might be other ways of saying it too, but those are the main ones that you're going to see in your real life as a math student. All right, so here's another theorem that we can prove, this time about divisibility. So that's kind of nice. So we're letting n be an integer such that 3 divides n, then 9 divides n squared. All right, so if we look at this, we got to be careful about what we assume, what we're going to show. Well, remember, the let n be an integer such that 3 divides n, that means we're assuming two things. We're assuming n is an integer, we're assuming 3 divides n, and then the then part of our theorem is our show part. We're going to show that 9 divides n squared. All right, and so again, my eventual proof, or our eventual proof, must flow from assumptions to conclusions. We start with our assumptions, our proof flows logically from there to our conclusions. However, when we're setting up our proof and when we're trying to figure things out, we don't have to work on it in logical order. We don't have to start with our assumptions, and once we get stuck somewhere, we say, okay, well, we have to sit here until we get to our next step. No, we can skip around. The thing is, you can think of this as planning a road trip, right? If you're planning a road trip, your final driving plan has to begin at your starting point and end at your destination, and all your steps have to be in order. However, when you're planning it, you can plan your trip in any order. It doesn't matter which part of the trip you're planning. The only thing you need to do is piece together your trip at the end of your planning so that it fits together nicely. So, all we're required at the end is we have to start at 3 divides n, and actually n as an integer is in there too, but I'm going to just have 3 divides n in there as your assumption. That's at the top there, and then way at the bottom there, you have 9 divides n squared, and then you have to fill in the steps in between. And again, you don't have to do it in order, but you can, right? You can start with 3 divides n and say, I wonder what the next step in my proof after that is. What does it mean, 3 divides n? Well, a reasonable thing to say is, well, I'm probably going to start with the definition, right? 3 divides n means that n is equal to 3k for some integer k. I'm allowed to use the definition. In fact, I got to use the definition. That's the only thing I can use when I'm saying 3 divides n. And and it may be hard to think, well, what do I go from here? Well, I don't know. So maybe I can look at the end and say, okay, what do I think my step right before the end is going to be? My last step is going to be 9 divides n squared. Before that, I'm probably going to be using the definition of divisibility right before that, except instead of with 3 divides n, I'm going to use the definition with 9 divides n squared. So the step right before that is probably going to be n squared equals 9 times, well, 9... I can't say 9 times k because I don't know if it's going to be the same integer k, but I know it's going to be n squared is equal to 9 times integer. Which integer? I don't know. We'll figure that out later, right? All right, so now I have part of my proof figured out, but there's a big gap in the middle where I have to somehow connect n equals 3k to n squared equals 9 times an integer. Well, if I have n equals 3k and I want n squared equals something, what I can do to get there is I can square both sides of that equation. So I have that n is equal to 3k. If I square both sides of that equation, I square the 3 to get 9, I square the k to get k squared, I got n squared equals 9 times k squared. And it looks like I'm almost there, right? Because I have n squared equals 9 times k squared. I want n squared equals 9 times an integer. All I have to do is prove that k squared is an integer, but I get that by closure, right? Because k is an integer. If I square it, I'm still going to get an integer. So there's my proof. I start with 3 divides n equals 3k for some integer k, n squared equals 9 times k squared is an integer, n squared equals 9 times an integer, 9 divides n squared. There's the outline of my proof. All right, so now we're ready to write it up. And remember, the only difference between the outline of our proof and the actual written version of our proof is we're making taking extra care to make our logic clear to our reader and doing extra things that are nice to our reader to show them where we are in the proof. All right, so first thing I'm going to do is, write the theorem. Let n be an integer such that 3 divides n, then 9 divides n squared. The first thing I'm going to do that's nice to my reader is I'm going to tell them what I'm assuming and what I'm going to show. So what am I assuming? To prove this theorem, we assume that n is an integer and that 3 divides n, and that I'm going to tell the reader, what am I going to show? Then we need to show that 9 divides n squared, right? So that way we know where to begin with the proof. The reader knows where we're going to end with the proof. And we're going to do exactly what we did in our outline. Since 3 divides n, we have n equals 3k for some integer k. We're just using the definition, right? The next thing we did was we took that n equals 3k and we squared both sides. By squaring both sides of the equation, we get n squared equals 9k squared. We're telling the reader what we're doing. We're letting the reader in on the logic that we're using to get to our next step. Right? Now, once we got there, remember we were worrying about closure issues. We know that k is an integer and that the set of integers is closed under multiplication. We're setting up our reader, letting them know that we're going to use closure under multiplication. Thus, k squared is an integer. Yay, k squared is an integer. Since k squared is an integer and n squared equals 9 times k squared, it follows that 9 divides n squared. Again, we're using the definition of divisibility. And that was what we're trying. And then I say, this concludes the proof. Because now we're reminding our reader that was what we were trying to show. If you look at the second sentence, it says, we then need to show that 9 divides n squared. We got to the step where 9 divides n squared. When we say this concludes our proof, we're reminding our reader that that was what we were trying to show. That's the end of the proof. All right, so now you're ready to work on the activities for this part. It's called Divisibility, and it's on a PDF file included with the video.